Hello world, welcome back. In this video, we are diving into the absolute foundation of digital electronics, logic gates. Every digital system, from the simplest remote control to the most advanced processors, rely on these basic components to make the decisions that they do. And in today's video, we are going to break down exactly how they work and how to read their truth tables. And we are going to look at the seven standard gates that you need to know. So let's get started. So we're going to look at the basics, highs and lows. So what does high mean and what does low mean? So in digital electronics, we use binary, the number system with base 2. And a high in digital systems is a 1 in binary and a low is a 0. So if we have a high voltage state or a high state or a 1 state or a true state, it's this. They all mean the same. So a high state, an on state, and a true state, they all mean the same thing. And then a low state, a zero state, an off state, and a false state, they all mean the same thing. So the logic gates would take these high or low voltage signals as their inputs, and then they'll perform some mathematical logic operations on them. And then they'll input a new high or low voltage signal. And then to track what happens in the gates, we use truth tables, like I mentioned before. So a truth table is just a simple chart that will show every single possible input combination and then the resulting output of that input combination. So let's get started with our logic gates. So the first gate that we'll be looking at is the NOT gate, and it's also called the inverter. And it's the simplest gate that's out there, mainly because it has just one input. And this part of the gate, the left part, is the input, and the right part is the output. It's the same for all gates. Every single gate out there, the left part is the input, and then the right part is the output. So this representation here is a truth table of our NOT gate. And as I'm sure you are now aware, this is the NOT gate. The NOT gate can just be described as a triangle with a ball at the right hand side, or a bubble, however you want to call it. It's just as simple as that. A triangle with a bubble attached to the right part. And it has just one input. So this representation here, like I mentioned before, is a truth table. So when a NOT gate has a 0 as its input or a low state as its input, it outputs a high state or a 1. And when it has a 1 or a high state, it outputs a 0 or a low state. So it just switches the inputs to the other value. And in binary, there are just two values. So if it's not a 0, it's going to be a 1. If it's not a 1, it's going to be a 0. So when the input is 0, it just outputs a 1. And if the input is 1, it just outputs a 0. But the NOT gate always outputs the exact opposite of the input. Now let's move on to the next gate. Looking at two other gates, the AND gate and then the OR gate. And then these gates, like the rest of the gates, they require at least two inputs. So for the purpose of these presentations, I'm just going to limit our gates to having two inputs. But this AND gate here could have had three inputs, or even four inputs, or five inputs. It doesn't matter. It just has to have a minimum of two inputs, same as the OR gate and then the rest of the gates that we are going to look at. So the AND gate is characterized by this symbol here, which is very similar to a D shape. And it has its inputs at the left hand side and its outputs at the right hand, just like the OR gates, which is characterized by a curve at the inputs and then a pointed shape at the output. You can say that the OR gate kind of looks like an arrowhead, and it has its inputs connected here and then the outputs connected here. So this is the truth table of the AND gate, and this is the truth table of the OR gate. So for the truth tables, for this two inputs AND gates, it's like this. If both inputs are zero, the output will become zero. If any one of the inputs is a zero and then the other one is a one, the output becomes zero. And the output only becomes one when both inputs are one. That's the characteristic of the AND gate. So for an AND gate, no matter no matter the inputs, as long as one of the inputs has a zero, the output will not be a one, it will be a zero. So the condition for the output being one is for every single one of the inputs to be one. So if this had been a three inputs AND gate, let's say I had three inputs, 1, 0, and 1, the output would have been 0. And if it had been a four inputs AND gate, 0, 1, 1, 1, the output would have still been 0 because not all the inputs were 1. So that's the characteristic of the AND gate. So you can once again think of the AND gate as a strict rule. It will only give you an output high when each and every one of the inputs is a 1. Now let's look at the OR gate. So for an OR gate, if any of the inputs has a 1, the output will be a 1. So in the first row here, both inputs are 0. That's why our output was a 0. In the second row and in the third row, one of the inputs is a 1. That's why we have our output being a 1. And in the final row, both inputs are 1. That's why we have this output here to also be a 1. So our OR gate is more flexible. You can also think about it like this, that it's going to give you a high if the first input or the second input is a high. So it doesn't really matter as long as one of them is a high, it will output a high. So if this had been a four input OR gate, which had three of the inputs to be 0 and only one of them to be a 1, the output would have still been a 1. Our OR gate will only give us an output of 0 when every single one of the inputs is a 0, as seen here. And our AND gate will give us an output of 1 when every single one of the inputs is a 1, as seen here. Now let's look at our next pair of logic gates. Next pair of logic gates are our NAND gates and then our NOR gates. And these gates are famously called the universal gates because you can get any of the other gates using a combination of these two gates. So for our NAND gates, it can be modeled as an AND gate that is fed into the input of a NOT gate. So with our two inputs AND gates being fed into the inputs of a NOT gate, this is the same as the NAND gate, but for simplicity's sake, it is just represented as a D shape or an AND gate with a bubble in front of it or a bubble at the output. So from this diagram here, you can just see that the output of the NAND gate is just the inverse of the output of an AND gate. So in our AND gates, we know that if it has any of the inputs to be 0, our output will also be 0. But if we are going to be looking at a NAND gate, we have to just invert that output. So for our NAND gate, if any of the inputs is 0, we'll have our output to be 1. And then for our output to be 0, all of our inputs have to be 1. Or you can just look at it as you you perform the operation with an AND gate and then you just invert it so that you do not confuse yourself if you do not understand the concept I mentioned before, that a NAND gate will only have its output to be zero when every single input is a one. And then for any other case, when at least one of the inputs is a zero, the output will be a one. So if we have a four input NAND gate and we have a one, a zero, a one, and then a one, what do you think the output will be? The output is going to be a one because at least one of the inputs is a zero. And it will only be true if it will only be true for the output to be a zero if every single input is a one. Like I showed here that our NAND gate is just an OR gate that's fed into a NOT gate. We can also say that our NOR gate is just an OR gate that's being fed into a NOT gate. So this is it. We have our inputs here and then our output here. So it's just the same idea, just being applied to a NOR gate. And once again, for simplicity's sake, we just represent the NOR gate as an OR gate with a bubble attached to the side where the output is supposed to be. So in our OR gates, the output was a high when at least one of the inputs is a high. So it's going to be the opposite case in this gate here. So for our NOR gates, the output is going to be a zero if at least one of the inputs is a one or a high. So in our first row, both inputs are zero. That's why our NOR gate outputs a one. That's this row here. But in every other case, the output is going to be a zero because in every other case, there's going to be at least one or one high state present in the input. So that's it for the NOR gate. So if we had a four input NOR gate and then we had one, 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 and zero, because at least one of the inputs is a one, our output would be zero. In this case, there are three inputs that are one, so our output would have been a zero. If it had been zero, 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 and one, it would still be the same thing because at least one of our inputs is a one, so our output would have been zero. For the output to be one, each and every single input has to be a zero for the output to be one. So let's move on to our next pair of logic gates. So now we'll be looking at our XOR gate and then our XNOR gate. Our XOR gate is also called the exclusive OR gate, and then our XNOR gate is also called the exclusive NOR gate. So this is the diagram for our XOR gate. It's given by an OR gate. It looks very similar to an OR gate. The only change is that we have an extra curve attached to the input. So that's the characteristic symbol or the diagram for an XOR gate or an exclusive OR gate. And from the name, that's how it operates. So it checks for exclusivity. What does exclusivity mean? It means that for it to output a one or a high, only one of its inputs should have a high. So if more than one of its inputs has a high, it will output a zero. That's what it's meant by it checks for exclusivity. That's why it's called the XOR or exclusive OR gate. So in our first row, we have both inputs to be zero, which does not satisfy our condition for a high to be met. So the output will also be a zero. In our second row and our third row, we have just one input to be one. So it means that our output will also be a one. And in our third row, we have more than one input to be a one. So it means that our output will be a zero. So that's it for the exclusive OR gate. It checks for exclusivity, meaning that just one input has to be a one for the output to also be a one. Now, our XNOR gate is seen as an XOR gate with a bubble in front of it. So taking the page out of the NAND and NOR gates, it can be modeled as an XOR gate that is being fed into a NOT gate. So this is our XOR gate if we break it, XNOR gate if we break it down further. But once again, for simplicity's sake, you just put a bubble in front of an XOR gate to represent the XNOR gate. So to make things very simple, just take it like this. An XNOR gate is just the output of an XOR gate that is inverted, just to make things very simple. Or if you don't want to make things simple, you can look at it also like this, that an XNOR gate has a high when the input does not have just one of them to be a high. Let me take that again. Our XNOR gates will have an output to be a high when the input does not have just one of them to be a high, or when the input does not have just one value being a high. Let's look at it in the truth table. So for the first row, we have two of our inputs being loose, and then that satisfies our condition. It's not just one of our inputs that's a high, so it means that the output will be a high. In our second row, we have just one input being a high. And in our third row, we have the same thing. We have just one input being a high. So it means that our outputs in the second and third row will both be lows or both be zeros. And in our last row, we have both inputs to be ones or high. So it means our output is also going to be a high, which satisfies our condition of not having just one input to be a high. Okay. So that's it for our XOR gates. But before I go on, I want you to check something for me. I'm going to answer it on, but I want you to check something for me. Assuming we had a three input XOR gate and we had our inputs to be 1, 0, and 1. A three input XNOR gate, sorry. And we had our inputs to be 1, 0, and 1. What do you think the output would be? I'm going to give you some seconds to think about it. I'm going to answer. So for our three inputs XNOR gate, because we don't have just one of our inputs to be a 1, the output is going to be a 1. If it had been this 0, 1, 0, then the answer would have been a 0, because we have just one input to be a 1. That's why the output is a 0. So let's look at the same cases in our XOR gates. And the condition for our XOR gates to have a high is for just one input to be a high. So if we have the same case 1, 0, and 1, our output would have been a 0 because we have more than one of the inputs being a high. We have two of them being a high. So the output would have been a 0. And then if we had 0, 1, and 0 as our inputs, our output would have been a 1 because we had just one input being a 1. Okay. So that's a wrap on our 7 basic gates: the NOT gate, the AND gate, the OR gate, the NAND gate, the NOR gate, the XOR gate, and then the XNOR gate. And like I mentioned, for these gates, they can have any number of inputs as long as those inputs are more than 2. It's only the NOT gate that needs to have a single input. So by combining these gates in different arrangements, engineers are able to build complex circuits that are capable of performing arithmetic and storing memory, as well as running entire operating systems. So if this breakdown made the logic gates clear to you, please like the video and subscribe to the channel. Leave a comment too if you have any questions about the truth tables or the symbols. Now, if you want to know how engineers design these massive circuits from scratch using the word problems or logic equations, you have to know how to build a truth table from the ground up. And we'll be looking at that in our next video. But for the meantime, please like, subscribe, and share. So I'll see you in the next one. Goodbye, world.